Hi friends, welcome back to Connect with Civil.
In this video, you can see how the design of axially loaded short column is done. Before stepping into the design procedure, let's have a basic understanding on certain things. As we all know, this is an RCC framed building. In this, vertical members are columns. To define columns, we can say these are compression members, the effective length of which exceeds 3 times the least lateral dimension. Axial compressive force will be predominant here. Based on the nature of loading, columns can be classified into 3 types. First one, axial loading applied concentrically. Here, there is no eccentricities with respect to the centroidal axis. That is, pure axial compression is acting. Second is the uniaxial eccentric loading. So, it is eccentric with respect to one centroidal axis. Flexure, that is bending moment, accompanies with axial compression. Statically, this is equivalent to a system consisting of a load applied with an eccentricity with respect to the longitudinal centroidal axis of the column. The third and the last one is a biaxial eccentric loading. Here, loading is eccentric with respect to both the axes. That is, along with axial compression, there will be bending moments in two perpendicular directions about the major and minor axis of the column section. So, this video deals with the columns with first type of loading condition, that is axial loading applied concentrically. For the columns located in the interior of symmetrical simple buildings, the eccentricities under gravity loads are generally of low order and sometimes neglected in the calculations. Such columns fall under first category. However, code specifies sufficiently conservative design to make the column capable of resisting nominal eccentricities. Columns can again be classified depending on whether the slenderness effects are considered significant or insignificant. Slenderness is a geometrical property of a compression member which is related to slenderness ratio, which is equal to the ratio of effective length to its lateral dimension, whereas effective length is the distance between the points of inflection, that is zero moment, in the buckled configuration. I'll explain the calculation of effective length and slenderness ratio later in the video. Slenderness ratio provides a measure of vulnerability to failure by elastic instability or buckling. The clause 25.1.2 says columns with low slenderness ratios, that is less than 12, are short columns and otherwise are long or slender columns. Short columns fail under ultimate loads where the material reaches its ultimate strength and not by buckling. Whereas the slender columns fail by buckling, large lateral deflection under relatively low compressive loads is common in such type of columns. Till now we have gone through certain things which forms the base for the column design. Now let's move on to the numerical example. Here is the question. Design the reinforcement in a 450 mm by 600 mm sized column subject to an axial load of 2100 kN under service dead and live loads. The unsupported length of the column is 3 meter and is braced against sideway in both directions. Use M20 concrete and Fe 450 steel. So let's have the given data now. First thing is, size of the column is mentioned as 450 mm by 600 mm. So here the major axis XX and the minor axis YY can be considered like this. So dx will be 600 mm, which is perpendicular to the XX axis, and 450
mm will be dy, which is perpendicular to the yy axis. Next is the axial load under service conditions. It is 2100 kilonewton. Unsupported length of the column is 3 meter and boundary condition is given as braced against sideway in both directions. Grade of concrete is M20 and grade of steel we have to use is Fe 415. As a first step, we have to check whether our column is a short column or a slender one. As I have mentioned, based on the slenderness ratio, we can decide it. So let's calculate the slenderness ratio first. So for that, we have unsupported length, that is the clear distance between the floor and the shallower beam into the column at the next higher floor level. That is 3000 mm in both directions. And lateral dimensions, dx is 600 mm and dy is 450 mm. We know the slenderness ratio is effective length divided by lateral dimension, where effective length is equal to effective length ratio k into unsupported length. Now substituting the value of unsupported length and lateral dimension, we'll get Lex by dx equal to kx into 3000 divided by 600, which is equal to 5kx. Since we don't know the value of k, let it be like this for the time being. So similarly, if we substitute the value of L and dy, we will get Ley by dy as ky into 3000 by 450, which is again equal to 6.67 ky. We have boundary condition as braced against sideway in both directions. That means our column is held in position at both ends. We have table 28 of IS 456-2000, which provides the effective length of compression members for different boundary conditions. Here I have not shown the full table. Whatever required for this question only I have considered. So in this, first column represents the boundary condition. Second column gives the symbol which helps us to understand the boundary condition better. Third and fourth columns give the theoretical and recommended values of effective lengths respectively. In this, L represents the unsupported length and the numerical part is the effective length ratio. Since the idealized boundary condition cannot generally be realized in actual structures, the code recommends the more conservative values for effective length ratios than the theoretical ones. So we can use the values in the fourth column. If you refer the table in the code, you can see first 3 rows represent our boundary condition. And since rotational restraints are not mentioned in our question, the recommended value of our effective length can be 0.65 to 1 L. Now let's check whether our column is a short or slender one. From table 28, we got the effective length is equal to 0.65 L to 1 L. Then effective length ratio K is equal to 0.65 to 1. We have slenderness ratio about x-axis is 5kx. Since kx is less than or equal to 1, our slenderness ratio about x-axis will be less than 12. Similarly, about minor axis, we have slenderness ratio as 6.67 ky. Since ky is less than or equal to 1, Ley by dy will be less than 12. Since slenderness ratios about both the axes are less than 12, we can conclude our column is a short column. Sometimes Eccentricities which are not arising out of structural analysis calculations act on the column due to various reasons such as accidental lateral loads, errors in construction, underestimation of slenderness effect, etc. For this reason, code suggests every column to be designed for a minimum eccentricity which is equal to the unsupported length of the column divided by 500 plus lateral dimension divided by 30 and subjected to a minimum of 20 mm. So, first we have to calculate the value of L by 500 plus D by 30, and if it is greater than 20, the calculated value will be the minimum eccentricity. If this is less than 20, then 20 mm can be considered as the minimum eccentricity value. So on calculation we will get Ex minimum is equal to 26 mm, which is greater than 20, and Ey minimum is equal to 21, which is again greater than 20. So our minimum eccentricities are 26 mm and 21 mm. At this stage we know our column is a short column and it has to be designed for the given axial load and the calculated values of minimum eccentricity. IS 456 has given an equation for the design of short axially loaded compression member if the minimum eccentricity does not exceed 0.05 times the lateral dimension. So let's check that condition first. 0.05 dx is equal to 0.05 into 600, which is 30 mm and is greater than Ex minimum of 26 mm. In the other direction, 0.05 dy is equal to 22.5 mm, which is again greater than Ey minimum of 21 mm. That means our column can be designed using the formula specified for axially loaded short columns. So we have the equation as Pu is equal to 0.4 FCK AC plus 0.67 Fi ASC. Here AC is the area of the concrete. So AC can again be written as AG is equal to ASC, where AG is the gross area and ASC is the area of longitudinal reinforcement of the column. On substitution and rearrangement, we will get the equation as 0.4 FCK AG plus 0.67 Fi minus 0.4 FCK into ASC. Here, Pu is the axial load on the member, that is 2100 into, we have to multiply it by a factor of 1.5, which is equal to 3150 into 10 raised to 3 Newton. FCK is the characteristic compressive strength of the concrete, which is equal to 20 Newton per mm square. AG is the gross area of the column section, that is 450 into 600. Fi is the characteristic strength of the compression reinforcement, which is equal to 415 Newton per mm square. ASC is the area of the longitudinal reinforcement for the column, which we need to find. So on substituting all other values and solving, we will get the value of area of longitudinal reinforcement as 3666 mm square. We got the area of reinforcement. Now we have to see the placement of longitudinal reinforcement. We have some code requirements for this. So here I have taken out the clauses which are in use for this type of column design. So first is regarding the number of longitudinal reinforcement. For a rectangular column, the minimum number of longitudinal bars to be used is 4. Next one is regarding the diameter. We should use the bar diameter greater than 12 mm. Next is the spacing of the bars along the periphery should not be more than 300 mm. We have clause number 26.4.2.1 which says the minimum nominal cover to be used is 40 mm or the diameter of the bar, whichever is greater. Now, keeping all these requirements in mind, we can consider a clear cover of 40 mm, 4 numbers of 25 mm dia corner bars and 8 mm dia stirrups. We can calculate the spacing at smaller side, that is 450 mm, as 450 minus 2 into 40 mm, that is cover, minus 2 into 8, that is the stirrup diameter, minus 2 into 25, that is 2 corner bars, which is equal to 304 mm and is greater than 300 mm. So obviously the spacing at other side also will be greater than 300 mm. So it is understood that intermediate bars are required at all the 4 sides. So this is how the longitudinal bars will be arranged in this case. Here you can see the circles represent the cross section of the longitudinal reinforcement, and there are 4 corner bars, and as per the spacing requirement we have provided for intermediate bars also. We know the diameter of the corner bars but yet to fix the diameter of the intermediate bar. Let's do that. The area of the longitudinal reinforcement we have calculated is 3666 mm square. Now we know the corner bars, 4 corner bars of 25 mm diameter is there. So let's calculate the area of corner bars. That is 4 into area of 1 bar gives you 1962.5 mm square. So the balance area will be the intermediate bars area, which is equal to the total area minus the area of the corner bars, which is equal to 1703.5 mm square. From this area you can find the diameter of the intermediate bars. So divide this area by 4 numbers into pi by 4 and taking the square root will give you the diameter as 23 mm. We can consider the standard size of 25 mm dia bars. Now we have 8 numbers of 25 mm diameters as longitudinal reinforcement in our column, that is 4 corner bars and 4 intermediate bars, all are of 25 mm diameter. So the actual area will be 8 into pi by 4 into 25 square, which gives 3927 mm square. So now we got the actual area. We have one more requirement specified by the code, that is the cross-sectional area of longitudinal reinforcement shall not be less than 0.8% nor more than 6% of the cross-sectional area of the column. Percentage of reinforcement is equal to total reinforcement area divided by cross-sectional area of the column, that is 450 by 600 into 100 will give you percentage of reinforcement area as 1.45%, which is coming in between 0.8 and 6. So we can take the longitudinal reinforcement as per our calculation. Since we have finished the design of longitudinal reinforcement, let's think about the lateral ties. We have few requirements specified by IS 456. The clause 26.5.3.2c along with an amendment says the diameter of the lateral ties shall not be less than 1/4 of the diameter of the largest longitudinal bar and in no case less than 6 mm. The amendment section you can see starting of the code just after the content section. So in our case, the diameter should not be less than 1/4 of 25 mm, that is 6.25 mm or 6 mm. So in this greatest 6.25 mm, which is the diameter of our lateral tie, we can adopt the standard size of 8 mm. Coming to the pitch, it shall not be more than the least of the following three distances. That is, the first one is the least lateral dimension of the compression member. Second is 16 times the smallest diameter of the longitudinal reinforcement bar. And third one is 300 mm. So our case, pitch should not be greater than 450 mm, 16 into 25, that is 400 mm, or 300 mm. From these three, we can consider the least one, that is 300 mm as our spacing. So we can have lateral ties of 8 mm dia at 300 mm center to center. Here comes the detailing part. So you can see the column section is marked as 450 mm and 600 mm. So longitudinal bars are marked as dots, 4 corner bars of 25 mm dia and 4 intermediate bars of 25 mm dia are marked. And lateral ties are 8 mm dia at 300 mm center to center. So here is a picture. You can see 8 numbers of longitudinal bars and 2 numbers of ties at each section, that is one enclosing all the longitudinal bars and another enclosing only the intermediate bars. We have finished our design. Now let's revise the steps. First step is to check whether the column is short or slender. For this, we have to find the slenderness ratio in both directions, and it is equal to effective length divided by lateral dimension, where effective length can be calculated by multiplying unsupported length with the effective length ratio. Effective length ratio can be taken from table 28 based on the given boundary conditions. If slenderness ratio is less than 12, it's a short column. Next step is to calculate the minimum eccentricity to be considered. E minimum is equal to greatest of L by 500 plus D by 30 or 20 mm. Now compare the minimum eccentricity with 0.05 times the lateral dimensions in both directions, and if values of E minimum for both directions are less than the same, we can design the section using the equation PU is equal to 0.4 FCKAC plus 0.67 FIAC. Find ASC from the above equation. Finalize the diameter of the corner bars and check the necessity of intermediate bars. Once the longitudinal bars are fixed, find out the actual percentage of reinforcement and check whether it's within the specified limit. Finalize the diameter and pitch of the lateral ties and their arrangement according to the specification. The final step is the detailing part.